Okay, we're on page 35. We're going to finish off reaction rates today and possibly start equilibrium. Page 35. 35. Okay, 35. We're down at the bottom of the page. You don't always have to do like the little skip counting if you don't want to. You can sometimes just go, oh, I have a half-life of 8 days. That pen doesn't work. Let's try a different one. I have a half-life of 8 days. What fraction will remain after 24 days? How many half-lives is 24 days? 3. 24 divided by 8 is 3 half-lives. So you can count that way. You can say after 1 half-life, you have a half left. After 2 half-lives, a quarter. After 3 half-lives, you have an eighth. So an eighth will remain. Is good? Okay. But we can also make this little rule here. The general rule for half-lives, this is not a formula anywhere though, so if you're like, this is too complicated for me to remember, because quite frankly, I can't remember it, like when I'm not thinking about it, but the fraction of A remaining is going to be equal to a half to the n, where n is the number of half-lives. So let's try the copper acetate question from that we did earlier. Okay, so we say the half-life is 12 hours and 12.70 hours. What percent, cut. Whoa, not good. Okay. Oh, okay, good. Phew. What percent remains after 64 hours? And this is not like a nice solving question, because you're like, how many half-lives is that? You can't really count them, yes? But you can do a division, and you can say, like, if this was a multiple choice question and you did your division, you could say that's really close to 5 half-lives, and then you could just estimate based upon that, right? Now, if you're doing this in a written response, which I don't think you will ever have to do, but just in case, you can say a half raised to the power of the number of half-lives is the fraction of, this is the decimal percent, remaining. And so in order to convert that to a percent, you then multiply by 100. I don't think it's very likely you're going to have to do anything this complicated. I think you're just going to have to do like, I start with 64. How many half-lives have passed if I've got 2 left? It's going to be like nice numbers that you can deal with nicely. Yes? Now, you should also be able to read a graph and use the information. So take a look at that graph there, example 7. What is the half-life of magnesium? Do those 3 questions, please. just guessing. I mean, I'm approximating. If you said 25, that would be okay. Yeah? What? Oh, that's a 40. Sorry, I just can't do things properly. Let's try that again. Either of those would probably be okay. I mean, you're estimating off a graph, right? Is that what you guys got? Yes? Excellent. Okay, so that's pretty straightforward. Ooh, the rate constant. Mm. Are you guys following what we're doing so far? Hello, come on in. Shh, pay attention to them. Stop talking. Are you guys coming by tomorrow as well? Oh, only the ones. Okay. Okay.
Yeah, I was gonna tell you to know. I didn't want to force you to know that.
Lon,
Do I get the wristwatch? Serious? Serious?
thank you. is wrong with me? Oh my God. Do you get the same thing? No, okay, never mind. I don't know what I'm doing here. Yes, you should use the half-life equation. Sometimes my brain is trying to make things too complicated. None of you guys ever do that, do you? All right, are we good? Okay, the answers are here anyway. There we are. Now, in the, I guess I should say on our next page, in the very unlikely event, or maybe even very, very unlikely event, that AP decides to give you a 0th order or a second order, don't panic, because you don't have a T1/2 equals whatever. You don't have that for second order. You can just use the integrated rate law equation for second order, plug things in, and be like, okay, we're starting at this initial concentration, decreasing to half, and you just plug everything in and that's it. Is good? Okay. So there's some exercises here. I don't know, do you feel like you need any time to work on those? Would you like some? Nah? Okay, moving right along then. We are on our last topic. Again, this is not a super common topic. This is not going to come up often. You may not see this at all on your AP exam. So you have to decide when you actually go to study how much time you want to devote to such a thing, right? Not a common topic. However, if you're going to university, you might need to do it, right? And so on and so forth. So we're going to go through it anyway. So we know what an elementary process is, yes? Okay. You cannot derive the rate law from an overall reaction, but you can derive the rate law. You can use the coefficients of each elementary step. So in an elementary step, you can derive the rate law for a reaction, okay? Yeah, this is page 42? Yeah, 42. So, you cannot find the rate law from the coefficients of the overall reaction. But if you want the rate law for any one step, you can use the coefficients, okay? So if we have an elementary step where we have one reactant, okay, one particle, that is known as unimolecular, yes? And the rate, you'll notice, what is the coefficient of A here? What's the coefficient of A here? 1. So our rate is Ka to the 1, because it's an elementary step. Okay, can't do that if it was an overall reaction, but because it's an elementary step, you can. Okay. We can have an elementary step which is bimolecular, has 2 molecules. Okay, and we have A plus A. So in other words, how else could we rewrite this? We could rewrite it as 2A, which means that A is going to be raised to the power of 2. Does this work for an overall reaction? No. What does it work for? Elementary step, okay? So if you have 2A that is bimolecular, if you have A times B, that is also called bimolecular. molecular. Each of these have a coefficient of 1, so each of these are to the 1, but you don't have to write the ones because, you know, it doesn't make any difference. Is good? Okay. Now, uncommon, but still occur from time to time, is the termolecular. Ter means 3. Okay, so you've got AAA. So you've got A to the 3. You could have A plus 2B. And you could say, okay, the A is going to have a coefficient of 1, the B, or going to have an exponent of 1, and B is exponent of 2. Here we got 1, 1, 1, so each A, B, and C are all raised to the 1. Straightforward enough? Okay, awesome. So you guys are going to write the rate law for each of the following elementary processes, and you're going to give their molecularity, which means unimolecular, bimolecular, termolecular. Okay? Yes? You don't have to worry about it for this. Okay? Yeah. Yes? Yes? No. If you're lucky, you'll get them back tomorrow. Right now, I have 87 quizzes in my possession. 87 quizzes and close to 120 labs, which makes me say bad words. I look at it and I'm like, oh. So I will do my best to get them back to you for tomorrow, but I'm not going to make any guarantees, okay? Which is one of the reasons why your test is on Tuesday, just in case I don't make that deadline. Are you getting the same answers as me? Yay! Yes? No. Because the order is for an overall reaction. I mean, you could say that this step is third order, this step is second order overall. Yeah. All right. Now, if you are given an overall reaction, when you're given an overall reaction mechanism, I don't know why I forgot the word mechanism. Each rate constant for each step, I should really rewrite this, for each step can be labeled with its own K value. I don't know why I wrote overall. So when you are given a reaction mechanism, each rate constant for each step can be labeled with its own K value. The K for step 1 is called K1. The K for step 2 is called K2. Shocking, yes? Okay. Sometimes an elementary process can be an equilibrium. Do we remember the term equilibrium? Equilibrium is where both the forward process and the reverse process occur at the same rate. And if that's the case, if you have both the forward reaction occurring and you have the reverse reaction occurring, you can see I do this sort of like little double harpoon arrow showing forward and reverse, then the K of the reverse reaction also has a designation. It is K minus 1. Are you talking over me, Armand? It's okay. All right, because I never talked over any of my teachers. I was so bad. I'm so sorry. Yeah. I look back and I'm like, oh my God, I was that person. Oh! Okay. Anyway, so we have step 1. And if you are going to have a slow step, be step 2, and you're expected to find out the reaction mechanism, your first step will be a fast equilibrium step. Because when you are at equilibrium, concentration of reactants remain constant and concentration of products remain constant. We're going to learn about that in equilibrium, but just believe me for now, okay? So you can label them. K1 is the forward, K minus 1 is the K for the reverse. And then of course we have a K2 for the second step, which only goes one direction, K3 for the third step, okay? Now, determining the rate law for the overall reaction from the mechanism. Yes? Yes, but I don't know what it is right this moment. We'll see if we come across it as we go through, okay? And if not, I will think about that. Yeah. So the rate determining step, as we know, it limits how fast the rate can go. Oh, that was so nice and rhymey. The rate determining step, as we know, limits how fast the rate can go. So any steps after the rate determining step have no bearing on the rate law. Yes? So our easiest situation is going to be if the first step is the slow step. Because does it matter that I've got some F here and that I've got some NO2 here? Those concentrations will not affect the rate. So I only have NO2 affecting the rate once. I don't have it affecting the rate here. Okay, because it affects it's unimolecular in the first step. At least the NO2 is, we've got one NO2. So if we were to write the rate law for the overall reaction, it is the same as the rate law of the first slow step, because that's it. Everything else doesn't matter. So you just say rate is equal to K1 NO2 times F2. And lo and behold, you are done. That is the rate law for the first step. It is the rate law for the overall reaction. Now, situation 2 is more complicated. Yes? What? The box at the bottom of, oh, up. The rate law. Oh God, that's a word salad, isn't it? Oh my Lord. Okay, the rate law for the overall reaction, this should be bold, is the rate law for the slow step. There we go. So get rid of these words here, okay? So the rate law for the overall reaction is the rate law for the slow step, but we have to express it in terms of reactants only, no intermediates. And that's easy if you're doing step 1 because there are no intermediates yet. Yes? No, there cannot be 2 slow steps because 2 steps are not going to be exactly the same speed, and whichever one is the slowest is the slow step. Everything else is fast in comparison to that. Yes? Okay. All right, situation 2, we have a slow step preceded by 1 or more fast equilibrium steps. This is a little more complicated because we cannot use intermediates in the rate law. So based on the proposed mechanism below, find the rate law for the overall reaction. And this is where you have to decide, do I care enough to really learn this? Because this is a pain in the ass, it's long, and it's complicated, okay? I'm gonna go through it today, and then you can decide whether it's worthwhile spending any time on. When the first step is slow, that's pretty straightforward, yes? So, here we go. Write the K's. So we have K1, K minus 1. We have K2. We are now going to rate the rate law for the slow step because that will be the rate of the also the law for the overall reaction, yes? And we're going to start with just intermediates and whatever because that's going to make, we're going to plug things in later, okay? So we have rate equals, and here is our slow step. So it's going to be the constant, or sorry, K2, because it's step 2 is the slow step, times the concentration of NO3 times the concentration of NO. Now we say, where am I going to get NO3 from? NO3 is going to come from the first step. NO3 is an intermediate, yes? So, what's going to happen? We're going to go back to our first step and we're going to say, what is the rate law of the fast equilibrium, forward fast equilibrium? So now we're going to go to our fast step. Rate, actually I'm going to call this rate 2, I'm going to call this rate 1, is going to equal K1 times what? Concentration NO concentration of O2. So we're just doing the rate law for step 1. Okay? We're also going to write the rate law for the reverse of step 1. So this is, we're going to call this rate -1. It's the reverse of step 1. So it's going to be K -1. Who are the reactants for the reverse reaction? NO3. So here we go. We have NO3. Now, one of the first things we're going to learn about an equilibrium is that in any equilibrium, this is true. The rate of the forward reaction is equal to the rate of a reverse reaction. That's what makes it an equilibrium. If you don't feel good about that yet, don't worry. We spend like the rest of the year talking about equilibrium. You will have months to feel good about that statement, okay? Just believe me for now that the forward and reverse reaction rates are equal when it is an equilibrium, okay? Equilibrium. That's what's equal in an equilibrium, is the forward rate and the reverse rate. So what that means is that these two things are equal, right? This is equal to that. So I can then write this bit here is my forward, and this bit here is my reverse, yes? So I can plug in my reverse stuff here. I can say, okay, K -1 NO3 is equal to that forward rate there, K1 NO O2 And do you remember how I said we cannot have an intermediate in our rate law? Could we solve this for our intermediate? Yes, we could. So let's solve for the intermediate, which is NO3. So now I'm going to rewrite my slow step equilibrium just so you can see it right here. This is our slow step. Rate 2 equals K2 NO3 times NO. That's what we did back at the beginning. And now I'm going to take this value and substitute it for NO3, okay? But as I do that, I am going to collapse all my K's into one K and just call it K, all right? So, and I'm going to combine like terms here as well. So we have rate 2 is equal to K2. I'm going to write down my K's to start with here. K2 times K1 over K minus 1 times NO3, which is NO times O2 times K minus 1, or I didn't keep them together, I'm sorry. This is the NO3 here, sorry. Here, why don't we put it all over top rather than, there we go. Is that better? There we go. Okay, and now we're going to multiply it by that NO that's right there. NO. And now we say, yuck to all those Ks. Let's just take those and make those a K. Yes? Times NO squared. Yes? Times O2. NO is a reactant. O2 is a reactant. So now we have the rate overall is equal to K times NO squared times O2. And that's it. You're done. Yes? No, I might have done something dumb because you know I always have. You just take all of these and you collapse them into one K. You say, that's just a K now. It doesn't matter what they all are, okay? Yeah. You just go, okay, I'm combining them all into one K. You can say K overall or whatever. It's a new constant, yeah, yeah. Yes? Could you still have the numbers? You could have all those, you could like write it as K2 times K1 over K minus 1 if you want to, instead of just writing it as K. It's the combination of those three constants. K is equal to K2 times K1 over K minus 1. This is K overall. Yeah? Yes? Shh. I would put it as 1K, but you could leave it as 3 separate Ks. It really doesn't matter. What they're looking for is they're probably just going to want this, and it's probably going to be a multiple choice question, and you're probably going to look at that and say, screw that, that's with 1 mark. Yes? Right? Now, that all being done, before I understood how this method worked, back when I was first teaching AP, I would look at this question. This is kind of a little cheat, but it doesn't work all the time. Okay? Watch this. I said, okay, I know that this is my rate of my slow step, and I know that I need NO2, NO3. Instead, I need to replace NO3 with reactants. Well, what do I need to get those? I need an NO and I need an O2. So what I would do is I would take these and I would substitute them instead of that. And guess what we get? We get NO squared times O2. Wasn't that faster?
Yes.
Did you follow that? So what I would do is I would say, what do I need to get NO3? I need 1 NO and I need 1 O2. So I would kind of be like, okay, so instead of NO3, I would have like concentration of NO times concentration of O2, that's my NO3, times the concentration of NO, and then I would take that and I would be like, okay, rate equals NO squared times O2. It doesn't work all the time though, and my brain is not big enough to know why. I think I knew why at one point, but I have forgotten. Yes? So yeah. So if you want to just take a risk on it, you can be like, okay, let's try, we have another example here. Let's just take another example here and see if it works. Let's see if it works here. Okay. Oh, this one's a nasty one. It's got 2 fast steps. You're never going to have to do this. Should we skip this one? Yes, you could do it. Like it's all worked out for you in the answer key, but I feel like it's too painful to do. Yes. Uh-huh. The cheat thing, yes. Yeah, which is why it's NO squared. Yeah, yeah? Okay, cool. All right, so like I said, it's here's a big horrible example. You can do it if you want to. There's some practice in here. Most of the practice are like fairly reasonable. So you might want to give those a try. Okay, why don't you guys give some of these a try while I go and get your equilibrium booklets for you. Okay? Why don't you just forget about that and say that's only 1 mark on the test? Yeah, right? And if they do something stupid, like put it on as a written response, that means nobody's going to know how to do it because it's one of those things where everyone's like, it's too hard, it makes no sense. Half the people won't even have learned it at all. Do you know what I mean? Right? So it's one of those things that's like scaled. Yes, exactly. Okay, nobody's saying anything, so go get pizza and answer key beside it. Ah.
Their background is on the guy who's speaking it like is there anything else? That's what I just said.
Did we run out? Okay, and then there's the book here. Did everybody get a copy of the book? Okay, yay. All right. Well, because you did all the AP stuff and all the regular book stuff. So that was more than that. There's no AP in there, but there will be later. I just haven't finished it yet. I'm still working on it. Oh my God. Okay. Okay, we're gonna watch a video and you can fill in the blanks as we go. Okay. It may take a while for the video to load because it doesn't like doing more than one thing at a time. So you're gonna open to page 1 and you're gonna fill things in. And I don't have a copy of the book, so you're gonna have to be like, okay, stop. Because I don't know when to stop because I don't have things to fill in.
Faster than. In this lesson, you will learn about dynamic equilibrium, the conditions required for dynamic equilibrium to be reached, and examples of systems at equilibrium.
Okay, I have paused it because we need to make sure it actually goes big because right now it's not big. There we go. Okay.
Imagine you are digging a hole. You got it? Imagine, as you are digging that hole, your friend is refilling it. If you are digging the hole faster than your friend, the hole gets larger.
Yes, so if you're digging the hole faster than your friend is filling it, the hole gets larger. Yes.
If your friend is filling the hole faster than you, the hole gets smaller. But if the two of you are working at the same speed, there would be no change to the size of the hole.
Let me know if you need me to go back or reiterate anything, okay? Are you good? What's spiky? Oh, the sounds? Oh. Here, let's see if we can maybe just turn the volume down a little bit. Maybe. We'll see.
The same concept can be applied to a reversible reaction.
Okay, that's too quiet. Sorry.
If the rate of the forward reaction
Okay, let's try this.
reactants to products is the same as the reverse reaction, products to reactants, the reaction is said to be at equilibrium. This is called a dynamic equilibrium because both processes are occurring simultaneously.
So this is different. Physics, you will come across static equilibria. Chemistry, we are always concerned with dynamic equilibria. Because in chemistry, if a reaction goes all the way and it doesn't go backwards, you're not at equilibrium. The reaction has gone to completion, okay? Both reactions have to be taking place. You have to be digging a hole all the time. Your friend has to be filling the hole all the time in order for you to be in equilibrium, okay? Chemical equilibria is always dynamic. Those reactions are always continuing to occur.
even though there is no overall observable change. For a chemical system, such as
No overall observable change. And it doesn't matter if you don't fill in all the blanks and whatever, as long as you get the general idea, okay? This was sort of meant to be like, take it home, do it, you know.
a reaction or phase change to be at equilibrium, it must meet two important criteria. First, it must be a reversible process.
Can you have an equilibrium if the process is not reversible? No, because the whole thing about an equilibrium is the forward rate and the reverse rate are the same. If the reverse reaction does not take place at all, it can't equal the rate of the forward. Yes? Okay.
Second, it must be taking place in a closed system. A closed system is one where there is no exchange of matter, only exchange of energy.
Okay, so closed system, you can exchange energy with the outside, but no exchange of matter.
An example of a reaction at equilibrium is the reaction of hydrogen and iodine in a closed container to produce hydrogen iodide.
Okay, see we've got hydrogen, we've got iodine, and we got hydrogen iodide.
At the start of the reaction, there is a high concentration of hydrogen and iodine, and the concentrations decrease as hydrogen iodide is formed. The concentration of hydrogen iodide increases as the forward reaction proceeds.
Is that making sense? You start with all reactants. You start with everything reactants. And then as the reactants get used up, you start making more products. So the reactant concentrations go down and the product concentrations go up. Yes. Yeah.
As hydrogen iodide is formed. The concentration of hydrogen iodide increases as the forward reaction proceeds. As hydrogen iodide is formed,
Further back.
hydrogen and iodine in a closed container to produce hydrogen iodide. At the start of the reaction, there is a high concentration of hydrogen and iodine.
Reactant concentrations are high, because what have I put in the container? Reactants. So they're high. I haven't put in any product, so there's no product yet. Yes? Okay, what's going to happen to the concentration of reactants? They're going to go down. What's going to happen to the concentration of products? It's going to get higher. Ooh, I want you to think about this. As concentration of reactants gets lower, what happens to the rate of the forward reaction? Concentration of reactants gets lower. What happens to the rate of the forward reaction? It decreases. What's the initial rate of the reverse reaction? 0, because how much product do you have? Nothing, so it cannot go backwards. Now, as the reaction proceeds, you start making product. So what's happening to the concentration of the product? It's increasing. What's going to happen to the rate of the reverse reaction? It's going to increase. So you start with your forward rate. My forward rate is represented by my gloved hand. Okay? And it's high, and the reverse rate is 0. Yes? Over time, I use up reactants, so my forward rate gets slower. I make products, so my reverse rate gets faster, and eventually the two rates become the same. Yes? So, is good? walking across the front Ms. Spence. It's okay, we're gonna have pictures and diagrams and things.
And the concentrations decrease as hydrogen iodide is formed. The concentration of hydrogen iodide increases as the forward reaction proceeds. As hydrogen iodide is formed, the reverse reaction is then able to occur.
You know what? If you, we could even just watch this video without filling in the sheet if you would like. Do you want to fill it in? Yeah, okay. No, you don't want to fill it in? So you can just watch. Okay, and if you want to fill it in later, you can go back, watch the video on your own and fill it in. So let's just watch and learn and not worry too much about filling in blanks, okay?
Over time, the concentrations of hydrogen, iodine, and hydrogen iodide remain constant.
Because when the two rates are the same, that means that you're forming product at the same rate as you're using up product, and so the concentration of product stays the same.
So what is happening here? The reaction of hydrogen and iodine to produce hydrogen iodide is occurring at the same rate as the decomposition of hydrogen iodide to hydrogen and iodine. So there are no observable changes, although both the forward and reverse reactions are occurring. This reaction has not stopped, but rather has reached dynamic equilibrium. What would happen to this reaction if the lid on top of the glass jar was open?
I want you to think about that. What if we took the glass jar that has the hydrogen, the iodine, and the hydrogen iodide, and we opened the lid? They're all gases. Hydrogen is not denser than air, iodine is denser than air.
Please pause the lesson to think about this and resume when you are done. If the lid was removed, the system is no longer at equilibrium as the reactants and products or matter would be able to escape the system. Liquid bromine equilibrates to form gaseous bromine at room temperature. Remember that this is not a reaction, but rather a phase change. Phase changes can also reach equilibrium.
Some people are still writing, so I'll give you a minute. Whatever makes you happy.
Under the correct conditions. As liquid bromine evaporates, gaseous bromine condenses. Since these two processes are occurring simultaneously at the same rate, there is no observable macroscopic change.
And what will the pressure be of the bromine above the liquid bromine, the gaseous bromine? What do we call that? We call that the something of bromine. What do we call the pressure, the equilibrium pressure of bromine over liquid bromine in a closed container? It's a gas, so it would be vapor pressure. So when you have hit this equilibrium state, and you see how there's a cap on it? Yes? You have hit equilibrium state, there's a cap on it. That means you are at the vapor pressure of bromine at that particular temperature. Yes? At whatever temperature it happens to be at, the vapor pressure for a substance will be different at any given different temperature. Okay? Think about intermolecular forces. If intermolecular forces are strong, will vapor pressure of a liquid be high or low? Tell your partner what you think. If the intermolecular forces are strong, will vapor pressure be high or low? Okay, I would like you to imagine a box or a bucket full of rocks, okay? And you have another box or bucket full of magnets. Yes? Which one has stronger intermolecular forces? The magnets. Now I'm going to shake this. Now they're both fairly full. I'm going to shake this bucket of rocks, right? Not like this, right? But like little. What's going to happen if it's quite full? What's going to happen? Well, what's going to happen to the rocks? I've got rocks in a bucket filled to the top. I start shaking it around like this. Some of the rocks are going to come out. Yes? Now, I have a bucket full of magnets. Okay? What's happening? They're going to stick together. Are any individual ones flying out? No, they're stuck to the ones below them. So which one has a higher vapor pressure in our analogy? The rocks, because more are escaping as gas particles, whereas the one with the stronger intermolecular forces, less molecules are able to escape at that same temperature. Does that make sense? Cool. So bromine, I would like you to think about bromine. Do you think that, what kind of intermolecular forces does it have? London dispersion forces. Please tell your partners what causes London dispersion forces. Okay, so what kind of forces? London dispersion forces. And what causes London dispersion forces? Temporary dipoles. What does the temporary dipole of one molecule do to the molecule beside it? It induces a dipole in the molecule beside it. Now, bromine on the periodic table is number 35. Okay, 35. So if you have Br2, how many electrons does it have if you have Br2? 70 electrons. Yes, each bromine has 35 protons. Each of a bromine has 35 electrons. So it has 70 electrons. So would you expect the London dispersion forces in bromine, Br2, to be greater or less than the London dispersion forces in fluorine, which has an atomic number of 9. So fluorine F2 would have 18 electrons. Bromine would have greater. Why is that? It has a larger electron cloud, and the more electrons you have, the bigger the electron cloud, the more charge difference you can get from end to end. So we say it is more polarizable. Yes? Are these words sounding familiar? Polarizability? Okay, so bromine is more polarizable because it has a larger number of electron clouds, and its electron cloud is like physically bigger than for fluorine.
Are occurring simultaneously at the same rate, there is no observable macroscopic change, but the system is in fact in dynamic equilibrium. In summary, a chemical system is said to be at equilibrium when the rate of the forward reaction is the same as the rate of the reverse reaction. There are no observable changes, but both directions of the reaction are occurring, so it is a dynamic equilibrium. Reaction. There are no observable changes, but both directions of the reaction are occurring, so it is a dynamic equilibrium.
Okay, I can't seem to like.
A dynamic equilibrium.
Oh, okay. Okay, so for homework, what I would like you to do is I would like you to do how about you do pages 40 and 41? And 46, 47. 40, 41, 46, 47. And if you have extra time, you can try some of the multiple choice questions from the review you picked up today. Okie dokie.
Really simple question, but
Yeah.
like for a diatomic molecule like those gas,
Yeah.
they don't share electron, right? They just be together.
They share electrons, yes.
Then how come they still have 35 each?
Oh, because this one has 35 and that one has 35.
I remember like covalent bond, doesn't it like share an electron to complete the
It completes the valence shell, but the thing you have to remember is when they're on their own, they do not have a complete valence shell. So it's not like they're losing electrons, they're just combining them.
Also,
Yeah.
diatomic molecules still have like complete valence shell without.
Yeah, so without being paired up, they don't have a complete valence shell.
Yeah.
Once they're paired up, 70 electrons each, then they'll have a complete valence shell.
Okay.
Yeah, yeah, yeah.
Miss Spence. I heard that tomorrow is a 5-period day.
Yes, it is.
What's the schedule for tomorrow?